In the next set of lessons, we will be looking at the application of quantum mechanics to simple systems. We will start with the simplest system, the particle in a one-dimensional box. We will determine the solutions to the time-independent Schrodinger equation for this system. Then we will see what information we can determine from the wave functions. The particle in a one-dimensional box, often referred to as the PIB, is one that is typically defined as follows. The box is defined as corresponding to locations between x equals 0 and x equals L. In other words, the length of the box is L. The potential energy V of the particle inside the box is a constant and, for convenience, taken as 0. Outside the box, at locations where x is less than or equal to 0, or at locations where x is greater than or equal to L, the potential energy is taken as infinite. Classically, the animation below summarizes the particle's trajectory. The derivative of the potential energy tells us how the net force acting on the particle depends on its location. In this particular case, since the potential energy is constant, the force is 0 everywhere inside the box. The potential energy is constant inside the box. The derivative of a constant is 0. When we say that the potential energy is infinite at a given location, it means that the particle cannot be found there since it has a finite amount of energy. In other words, a PIB is one that is classically expected to move at constant speed inside the box. It doesn't have enough energy to go to the left beyond x equals 0 or to the right beyond x equals L. It's confined in the box from x equals 0 to x equals L. Let's solve the time-independent Schrodinger equation for the particle in a one-dimensional box problem. The equation is h hat psi equals E times psi, where h hat is the Hamiltonian operator and E is the energy. Solving this equation means finding the set of functions psi that will satisfy the equation. For a one-particle system confined to move in just the x-axis, the Hamiltonian operator is the kinetic energy operator, which takes the second derivative with respect to x, then multiplies by negative h bar squared over twice the mass, plus the potential energy operator V. For the PIB problem, the potential energy is 0 inside the box, so the Schrodinger equation simplifies to negative h bar squared over 2m times the second derivative of psi with respect to x is equal to E times psi. This is an example of what's called a second-order differential equation. It's second order because the highest order derivative involved in the equation is a second derivative. This particular type of differential equation has a simple solution. Psi can be written as e to the sx, where s is a constant. Let's verify. Here's the left-hand side of the Schrodinger equation. Let's substitute e to the sx for psi. We take the derivative of e to the sx twice, then multiply by negative h bar squared over 2m. The second derivative of e to the sx is s squared times e to the sx. Now let's do a substitution for the right-hand side. E times psi is just e times e to the sx. Equating the substituted expressions for the left and right-hand sides gives us negative h bar squared over 2m times s squared times e to the sx is equal to e times e to the sx. We can see that e to the sx cancels from both sides. This means that negative h bar squared over 2m times s squared is equal to e. Initially, we just assumed that s is some constant. Now we can see that the value of the constant s depends on what the energy of the system is. Rearranging this equation, we see that s squared is equal to negative 2me over h bar squared. We can see s squared is a negative number. Note that 2me and h bar squared are all positive numbers. Since we're interested in s, not s squared, we write negative 2me over h bar squared as -1 times 2me over h bar squared. So s is equal to the imaginary number I, which is the square root of -1, times plus or minus square root of 2me over h bar. Square root of 2me over h bar is just another constant, so let's call it k. Then s will just be equal to plus or minus I times k. In other words, for a given energy, there are two possible values of s for which e to the sx will satisfy the differential equation. E to the sx can be e to the positive ikx, or it can be e to the negative ikx. Therefore, we say that the general solution to our differential equation is a linear combination of these two functions. You can verify that if we multiply each of these functions by a constant, then add, the resulting function would be a solution to our differential equation. Okay, so here's what we have so far. The general solution for the Schrodinger equation inside the box is psi equals a linear combination of e to the ikx and e to the negative ikx. Outside the box, psi is 0. Remember that the square of the absolute value of psi is a probability density function. And we defined our system such that we're not allowing the particle to be outside the box by making the potential energy infinite outside the box. Recall that psi must be continuous, so the expression for psi inside the box must approach 0 as x approaches 0 and as x approaches L. Substituting 0 for x, we get C1 times e to the ik times 0 plus C2 times e to the negative ik times 0 is equal to 0. Similarly, substituting L for x, we get C1 times e to the ik times L plus C2 times e to the negative ik times L is also equal to 0. These two conditions are called boundary conditions, and as we are about to see, these lead to restrictions on what C1, C2, and K could be. Let's look at the consequence of the boundary condition that psi must be equal to 0 at x equals 0. Remember we said that C1 times e to the ik times 0 plus C2 times e to the negative ik times 0 must be equal to 0. E to the power 0 is just equal to 1. So the boundary condition simplifies to C1 times 1 plus C2 times 1 equals 0. It's easy to see that C2 must be equal to negative C1. Let's go back to our general solution. We now substitute negative C1 for C2. We can factor out C1 and get psi equals C1 times the difference between e to the ikx and e to the negative ikx. Using the Euler formula, e to the ikx equals cosine kx plus I sine kx, we can show that e to the ikx minus e to the negative ikx is just equal to 2I times sine of kx. We can lump the constants C1 and 2I into just one constant and call it A. So now we have narrowed down the solutions to our Schrodinger equation to a function of the form psi equals A times the sine of kx, where A is a constant. What about the boundary condition at x equals L? Remember that we've just narrowed down our solutions to those that are of the form psi equals A times sine of kx. If we substitute L for x, we get A times sine of kl, which must be equal to 0. Now there are two ways A times sine of kl can be equal to 0. Either A is 0 or sine of kl is equal to 0. But we cannot let A be equal to 0, because that would make psi equal to 0 everywhere. In other words, regardless of what x is, psi would be 0 if A is 0. If psi is 0 everywhere, that would mean the particle is nowhere to be found. Therefore, we must insist that sine of kl be equal to 0. This means KL, the argument of the sine function here, must be either 0, a multiple of pi, or the negative of a multiple of pi. We can further narrow down the acceptable solutions. We cannot let KL be equal to 0. This would mean that k is equal to 0 since L is not 0. And if k is 0, that would mean a function that is 0 everywhere. Therefore, KL must be equal to n times pi, where n is a non-zero integer. Rearranging this equation, it's easy to show that k is equal to n pi over L. In other words, we now have a restriction for k. We can say that k is quantized. We call n the quantum number. The quantization naturally arises from the mathematics when we apply the boundary condition. So, from psi equals a times sine of kx, we can further narrow down our acceptable solutions. They must be of the form psi equals some constant a times the sine of n pi x over L. We can specify a complete set of eigenfunctions for an operator by including only functions that are linearly independent. What do we mean by linearly independent? We say that two functions are linearly independent if we cannot write one as a constant times the other. Consider the set of eigenfunctions of the Hamiltonian operator that we have so far determined for the particle in a one-dimensional box. From the general solution to the Schrodinger equation, we've narrowed down the acceptable solutions to psi equals some constant a times sine n pi x over L, where the quantum number n must be a non-zero integer. Let's compare psi for n equals 2 and n equals negative 2. Psi for n equals 2 is a times sine of 2 pi x over L, and psi for n equals negative 2 is a times sine of negative 2 pi x over L. Since sine is an odd function, we can see that psi for n equals negative 2 is just the negative of psi for n equals 2, or negative 1 times psi for n equals 2. The two functions are not linearly independent. We say that they represent the same physical state, and we only need one of these two functions if we want to list a complete set of eigenfunctions for the Hamiltonian operator. What this means is that we can choose for our complete set only those wave functions for which the quantum number n is a positive number, positive integer. We don't have to. There is nothing wrong with choosing only those wave functions for which n is a negative integer. In fact, we can mix and match if we want. It's just convenient to just choose positive integers for quantum number n in this particular case. Since the square of the absolute value of psi is interpreted as a probability density function, its integral over all possible locations must be equal to 1. In other words, the integral of the square of the absolute value of psi from x equals negative infinity to positive infinity must be equal to 1. This is called the normalization condition. We can break up the integral into three parts. Outside the box, at x less than 0, psi is 0. So for the integral from x equals negative infinity to x equals 0, we plug in 0 for psi. Similarly, at x greater than L, which is also outside the box, psi is also 0. So for the integral from x equals L to x equals positive infinity, we plug in 0 for psi as well. Finally, for the interval x equals 0 to L, we plug in a times sine n pi x over L for psi. The first and third terms are obviously 0. We can solve for the absolute value of a, and we should find it to be equal to the square root of 2 over L. So, we can summarize a complete set of wave functions for the particle in a one-dimensional box with this expression. Psi equals square root of 2 over L times sine of n pi x over L, where the quantum number n is a positive integer. Note that we could multiply sine n pi x over L by negative square root of 2 over L instead of square root of 2 over L. Remember that we just need to multiply it with a number whose absolute value is equal to square root of 2 over L. In fact, we could use any complex number whose absolute value is square root of 2 over L. For a given n, we can write any one of these three expressions of the function as a constant times the other. They are not linearly independent. We only need to choose one of them to be part of a complete set. Using positive square root of 2 over L is just a matter of convenience. Note that if we take the square of the absolute value of any one of these three expressions, we get the same probability density function. In other words, the quantum number n uniquely defines the state of the system. There isn't just one correct way of mathematically expressing the wave function. We have just shown that a complete set of eigenfunctions of the Hamiltonian operator for the particle in a one-dimensional box can be written as psi equals square root of 2 over L times sine of n pi x over L, where the quantum number n is a positive integer. In the process of deriving this expression, we substituted n pi over L for k, which we identified as being equal to the square root of 2me over h bar. Here, m is the mass of the particle and E is the energy. From these two expressions for k, we can show that the energy is equal to n squared pi squared h bar squared over 2ml squared, or n squared h squared over 8ml squared. Therefore, we can see that energy is quantized. Note that it doesn't matter if we use positive or negative values for n. For example, a function for which n is 2 and a function for which n is negative 2 are not linearly independent. We've seen that. They correspond to the same probability density function. Here we see that they correspond to the same energy. As we said earlier, they represent the same physical state. You will recall that the concept of energy quantization was needed to explain phenomena that could not be explained by classical mechanics. Here we can see that energy quantization arises naturally from the mathematics based on the postulates of quantum mechanics.